let's talk about math. So we only have, just so you guys know, the only new material we have left to talk about is today and then next Tuesday, because we don't have class on Monday because it's a holiday. So today we're going to talk about exponential functions, and Tuesday we're going to talk about logarithmic functions, and then Wednesday and Thursday we'll review for the final, which will be due Thursday night. I'll probably extend it so you can turn it in Friday during the day, but I do need you all to turn it in relatively on time so that I can get it graded and actually give you grades for your actual grade for the entire course. Speaking of grading, I still have to finish. I was grading you guys' homework earlier today, and then I got busy doing something else. So I'm almost done grading the homework assignment that you turned in on Tuesday. And we'll grade the one you guys turned in today, and we'll grade the quiz. Yeah, okay, enough about me. So exponential functions. An exponential, got the L there. An exponential function has the form y equals b to the x power, or we could also write as f of x equals b to the x. Just something I've noticed, not from you guys, but from other students this quarter, is I've had a few students in like higher level math classes not say things correctly. So like I've had students say like this is y equals bx. It's really important to say the to the part. If you don't say b to the x and you just say bx, people are going to think you mean multiplication. So as I'm sure you all have noticed, I don't want to say stickler, but I am kind of a stickler for correct words, correct notation, because we want to convey the meaning that we actually want to mean. So when you say something, when you read something like this, you really should say the words in your head or out loud, y equals b to the x or f of x equals b to the x. And then there's a couple restrictions on what b is allowed to be. Pun intended. B has to be positive, so greater than 0, and b can't equal 1. And b is also called the base. And the reasons that, well, the reason b can't equal 1 is because 1 to the x would always just be 1. And it's not that that's undefined or anything, it's just not a very interesting exponential function. It's not exponential, it's actually a constant horizontal line, right? Y equals 1 is the horizontal line. So, and then the reason b has to be positive is because if you had a negative number, for example, let's say you had, let's call it a non-example actually. A non-example of an exponential function would be something like y equals -9 parentheses to the x power. This is still something, in fact, if you want to go look at it on Desmos, I highly encourage you to. The problem with something like this, though, is that it's not defined for every possible value of x. For example, if x were equal to the 1/2, then we would have -9 to the 1/2 power, also known as the square root of -9. And as we've talked about a few times, square roots of negative numbers are not real. So the reason we don't think about having negative bases for exponential functions is because they aren't defined everywhere. They have a restricted domain, is another way of saying that. Whereas any of these examples, y equals 2 to the x, y equals 3 to the x, y equals 1, g of x equals, sorry, f of x. People interchange y and f of x without even noticing it all the time. G of x equals 1/5 to the x, y equals pi to the x. As long as the base is a positive number that is not 1, it's valid. Square root of 2 to the x power, 2/7 to the x power, 5/3 to the x power. All of these are valid exponential forms that are defined everywhere, meaning no matter what value you pick for x, there is some real number output. So we're going to talk about how to graph things like this. And the nice thing is really, they're not that hard to graph, which is great. It's always great when things aren't that hard to graph, right? Graphing is one of those kind of things that some people are, a lot of people often are like, oh, graphing is the worst. And I won't lie, sometimes graphing is the worst, but whether or not it's the worst, if you continue taking math classes, you are going to be doing a fair amount of it. So even though graphing, you might not love it, you are going to want to practice it because it comes up a lot. So let's take a look at some examples. I mean, what would this class be without examples? Sorry, I've got all kinds of things over here. Yeah. Wow, that's a blurry looking page there. So let's graph y equal to 2 to the x. And it's interesting. So, I know why. All right, learning things, still learning things. Even an old man can learn new tricks. All right, so let's graph this. Typically, we're not going to do what we're about to do for 5, but since this is the first time we together are graphing an exponential function, let's do it by plotting some points. So I'm going to pick some nice values for x. Now, technically, you could pick any value for x, and there should be an output. But I want to pick things I actually know how to do without a calculator. So I'm going to pick values of x that are like 0, 1, 2, 3, maybe some negative numbers too, -1, -2, -3. So that when I graph this thing, well, that's not the most perpendicular looking axis I've ever drawn. Oh well, we'll live with it. Yeah, that's a little more crooked than I usually like to try and draw it. Again, usually I wouldn't encourage all of you to draw all these little marks, but I want to draw this one a little more precisely than I often would. So that's what I'm doing. So we're going to plug in these numbers to find what the y value is. And let's start with 0. So y is going to be 2 to the 0, which we all know is what? Everybody, all at once, the number is this many, right? Not this many, this many. Yeah. So right, 2 to the 0 is 1. Right, yeah, thanks. And 2 to the 1 is 2. Right? Anything to the first power is the same. So I would say it's not necessary to find all these values in general. And this is not how I'm going to have it. It's not how I'm going to ask you to graph things. I'm just doing it this way to show you how you could do it if you wanted to do it this way, or if you needed to do it this way. So 2 squared is going to be 4, and 2 to the third is going to be 8. Let's do the negative powers. So 2 to the negative 1 is just the reciprocal, which is 1/2. 2 to the negative second is the reciprocal of 2 to the positive second, which is 1/4. And 2 to the negative third is 1/8. And again, I would recommend when you see a negative power, ignore the negative for a second. When I think of 2 to the negative third, I really think, oh, what's 2 to the third? It's 8. So 2 to the negative third is the reciprocal of 8, which is 1/8. I will also mention, because this came up earlier today, whenever you take a positive number to any power, the output, the result is always positive. I'm going to say that again. A positive number to any power is always positive. It cannot end up being a negative number. So if I plot these points, let's see, I get 0, 1, I get 1, 2, I get 2, 4, I get 3, 8. That is, yeah, that's 8 there. Yeah. I get -1, 1/2. I'm not going to plot all these ones to the left because they start getting just small, right? -2, 1/4, etc. How small do they get? Well, I did say a positive number to a power always has to be positive, and that's true. So they should always be larger than 0. Here's kind of one way you can justify that to yourself. Let's say we went way far to the left. Like, let's say x was equal to -1,000. 1,000 is kind of like my go-to choice for a really big number. It's not that big, but it's big enough that it's kind of, we can kind of see what happens. So y would then be 2 to the -1,000 power, or as I would prefer to write it, 1/2 to the +1,000 number. And I don't know what 2 to the 1,000 number is, but I know that 2 to the 10th power is about 1,000. 2 to the 10th is 1,024. So 2 to the 1,000th power is 2 to the 10th times 100, which is 2 to the 10th to the 100th power, which is approximately 1,000 to the 100th power, or 10 cubed to the 100th power, or 10 to the 300th power. That's a lot of zeros, right? That is literally 10 times 10 times 10, 300 times, which is a 1 with 300 zeros behind it. That's a huge number, which means 1/, that number is a super duper small number. Very small, almost 0. Very, very small. Okay, so all I'm trying to point out here is that as you go further and further left, your values for y get closer and closer and closer to 0, but they don't ever actually equal 0, right? Even though it's very small, it's definitely not 0, right? 1 over a positive number is still a positive number. So what happens as we go to the left is we just get asymptotically closer to 0. That's what it looks like. Here's our graph of y equals 2 to the x. And I will point out just a couple things. Every exponential function will have a horizontal asymptote. And if we have not shifted it up or down from its kind of very normal, like, so this is kind of like the base case, right? This is the standard way of writing it. If you haven't shifted it up or down, then the horizontal asymptote will be y equals 0. And I often abbreviate this as H, capital HA for horizontal asymptote. And it's going to be, you can't just say 0, you really need to write y equals 0. So there's a horizontal asymptote. I will also mention, just because it is worth mentioning, this graph does not have a vertical asymptote. There are no vertical asymptotes. The other thing I want to mention is that there is always going to be a y-intercept. Yeah. And again, if you haven't done any shifting, right, if it's just kind of the base case here, the y-intercept is always going to be the point 0, 1. That will obviously change if we shift it up or down or left or right. And we have no x-intercepts. Again, that's not going to be true if we shift it down. If we shift this thing downward, it will cross the x-axis. And then the lights, I'm dancing around. Okay, anyway, sorry. So last thing about this that I'm going to make note of is the domain and the range. So the domain is the set of all possible x values. And I should say the domain typically for a function is all the things x is allowed to be. And here, there aren't any exclusions, right? There are no domain restrictions. X can be any real number. So the domain would be all real numbers, which we write in interval notation as a set from -infinity to infinity, with parentheses because you never include infinity because it's not actually a number. The range, on the other hand, is the set of all possible y values. In this case, y can be any positive number, right? There's always a way to pick an x value to get the corresponding positive y value. So the range would be all positive numbers, or written in interval notation, the set from 0 to infinity. Again, we use parentheses because we don't actually want to include 0 because the function can never actually attain the value of 0. It can be any number that is larger than 0, but not 0 itself. And a quick kind of note about that. I've seen people do this before, and I want to make sure you don't. So if I said the range was all numbers greater than 0, I would have seen a lot of people say, oh, well, that's everything starting at 1. So people have written incorrectly that the range was from 1 to infinity, including 1 because, right, it's bigger than 0. But that's leaving off a lot of numbers. It's leaving off everything that's between 0 and 1, like 1/2 and 1/3 and 1/5 and 1 over pi and anything that's right 0.997. So what I'm trying to say here is don't limit your thinking to only integer numbers. If you want every real number that's greater than 0, you need all the fractions and irrational things that are between 0 and 1 as well. So the range is not everything from 1 inclusive to infinity. The range is everything from 0 exclusive to infinity, which on the number line looks like, hey, there's 0, and I don't want that, but I do want everything to the right of it. And there's definitely a lot of space between 0 and 1. So we want to make sure we include all those numbers. Okay. So yes, we took a lot of time graphing this, right? It's definitely like we did the whole kind of thing very nicely. But now I want to talk about the way you really should graph this. And do I want, let's see, do I have, I kind of have, okay, let me do one more longish example and then we'll talk about the way we're really going to graph it. So the only thing that's going to be possibly different than that kind of shape that we just saw is if the base happens to be a number that's between 0 and 1. So in this previous example, if the base, or I should say not if, the base was larger than 1, right? The base was 2. If the base is larger than 1, you're going to have a graph that gets larger from left to right, which we call an increasing function. On the other hand, if your base happens to be between 0 and 1, so if our base B is between 0 and 1, so 0 less than B less than 1, our graph, instead of increasing from left to right, our graph will be decreasing. And again, whenever someone says a function is either decreasing or increasing, it is always implied they mean when you look at it from left to right. You're never, ever, ever, I should say, almost never, ever, ever talking about looking at a graph from right to left. We're always talking about from left to right. Left to right. So for example, lines that have positive slopes are increasing from left to right. I don't really need to say left to right. I should stop saying left to right. And lines with negative slopes are decreasing. Okay, last time. So let's look at graphing this. Let's try f of x equal to, say, 1/3 to the x power. Now, one way to think about this, and the previous one, is if you look at something like 2 to the x, as the exponent gets larger, the result also gets larger, right? 2 squared, or I should say, right, if you increase the power, so 2 squared, and then it gets bigger if you do 2 cubed, right? Because you're multiplying by another 2. So every time you increase the power, you have more 2's you're multiplying by, and the number gets bigger. On the other hand, if you're graphing something like 1/3 to the x, as you increase the power, that means you're going to multiply by more 1/3s. But multiplying by 1/3 makes a thing smaller, closer to 0. So that's why this function, as x increases, right, as we go from left to right, that's how x is getting bigger from left to right, the y values are going to get smaller because you're going to keep multiplying by more and more occurrences of 1/3, which is going to make it smaller. But let's plug in a few numbers just to see, and we'll try to keep it not too crazy. So this is probably the last time we'll make a table for this particular type of function. And let's do 0, 1, and 2, and -1 and -2. So again, if you plug in 0, anything to the 0th power is, wow, that's terrible. I hate myself right now. I am disappointed in myself for accidentally writing that down. It's definitely not 0. Ooh, awful. It is 1. Anything to the 0th power is 1, not 0. Like, how do I like black that out? Okay, anyway. So 1/3 to the 1 power, well, anything to the 1 power is just itself. And 1/3 squared, you can either think of it as 1/3 times 1/3, or it's 1 squared over 3 squared. Either way, that's going to be 1/9. And I will encourage you to notice that 1/9 is smaller than 1/3, right? We're getting closer to 0 as the power of x is getting larger. 1, and then 1/3 is smaller, and then 1/9 is even smaller. And you could do 3. 1/3 to the 3rd power would be 1/27. Let's go the other direction. What's 1/3 to the -1 power? That's a good question. I'm sure you guys know the answer. Oh. 3, exactly. Right, it's the reciprocal of 1/3, which is 3. And 1/3 to the -2nd power, you can think of it as the reciprocal of, so I'm actually going to think of it this way. I'm thinking of it as the reciprocal of 1/3 squared. I'm doing the negative power first to get rid of the fraction part. That's going to be 3 squared, which is 9. So you can see, oh yeah, the left values of x are large, and as we move to the right, the values, I should say, as the left values of x give y values that are large, and as we move to the right, the y values get smaller and smaller and smaller. God, this feels like so much work writing all these little marks. I do not want you to have to do that. But let's just graph this. So at 0, we get 1. At 1, we get 1/3. At -1, we get 3. And when x is -2, y is 9. So there is the shape of our graph. And again, I would point out horizontal asymptote is y equal to 0. And the x-intercept is 0, 1. Sorry, the y-intercept. Wow, y-intercept is 0, 1. Good job, Jamie. Okay. And the domain is still everything from -a to infinity, and the range is still all the positive values from 0 to infinity. And the main reason I'm making note of that is because these are things that are generally true about exponential functions. Okay, but now let's get to the real meat. How do you actually want to graph these things if you don't want to spend like a good 5 minutes plotting all these, I was going to call them dumb points, plotting all these inconsequential points? Well, here's the thing. Exponential functions all have the same sort of shape. So if I want to graph something like, I don't know, graph y equal to 4 to the x, I'm going to graph it by thinking about the horizontal asymptote, which is y equal to 0. I'm going to think about the holy smokes, the y-intercept, which is 0, 1. And I'm just going to remind myself, well, since my base is larger than 1, it's increasing from left to right. And I don't really think you really need to write any of this down, save you should write down or make note of the intercepts, as I usually encourage you to do. So if I was graphing this, like, okay, I've got the point 0, 1, and then it's got the usual exponential shape. I'm just going to draw it like this. Done. If someone asks you about the domain or the range, you should also mention that. That's it. Now, some people are not comfortable with this being all the work they show. And I understand that because usually I'm expecting people to show more work, but this is kind of one of those times when we don't really have to. If you did want to do one thing though, so some people do like to include 1 or 2 additional points. You can include 1 point to the right, say when x is 1 and y is 4. And you can include 1 point to the left, say when x is -1 and y is 1/4. I will not require you to give me those points, but you can if you want to. The only other thing you should really be aware of is that the larger the base, the steeper the graph. But so I want to really kind of make it a point though. I didn't draw this in a way that looks any steeper than my 2 to the x graph. In fact, my 2 to the x graph probably looks steeper. I'm not a big stickler for real exactness here, right? You just have to kind of get the right shape and then maybe plot another point if you really, really want to. So if I was asked to graph something like y equal to 5 to the x, for example, if I was graphing it on a different coordinate system, I would graph it virtually the same. Like, okay, y equals 5 to the x, draw the usual exponential shape. There you go. There's my y. Now, is that the best one I've ever graphed? Probably not. I could probably be a little bit more exponential in my look. So I might try, I might be like, okay, James, you did not a great job on this one. Let's try it one more time. Because it should get steep very fast as you move further and further to the right. Now, for comparison, let me show you guys some Desmos. If I can remember how to do it. Oh, I'm like, there's the button right there in my face. It's the new share button, which is literally highlighted in green. My brain doesn't want to see it. So let's look at Desmos here. So let's graph a couple of these just to compare them. So here's y equals 2 to the x. Okay, increasing from left to right. And if you zoom out, you can see right, it gets super duper duper steep. But I will also highlight does not have any vertical asymptotes, right? There is no vertical line that's like a wall for it. It just keeps getting taller and taller and taller as the x values get larger and larger and larger. And then if you graph something like y equal to 4 to the x, it's much steeper. Or y equals 5 to the x. Oops, not 5 to the 5, 5 to the x, even steeper. But they all have the same general shape of increasing from left to right, unless your base is between 0 and 1, like when we did 1/3. There's y equals 1/3 to the x, which is decreasing from left to right. Someone asked a question, why does this, so I wouldn't call it a line, first of all, I would call it a curve. Anything that's not a straight line, we typically try to call a line, a curve, not a line. But sorry, that's not what I meant to do. I meant to go back and share my other screen. Ooh, good job. Okay, so the question was, why does this curve go from left to right and the other problem from right to left? Sure, I can definitely talk about what asymptote is. So the reason why, and so when you say from left to right, I assume you mean why does this one get bigger from left to right as opposed to this previous one that got smaller from left to right? And the reason for that is because of the base. So in this example, the base was less than 1. And that's going to mean it's going to decrease from left to right, because as you let the x value be larger, the y value, like if x was 3, f of 3 would be 1/3 cubed, which is 1/3 times 1/3, times, well, 1/3 times 1/3 times 1/3, which is 1/27. So as the x values get bigger, 1, 2, 3, the y values get smaller. Whereas in our first example, as the x values get bigger, the y values also get bigger. So that's why when your base is larger than 1, the graph is increasing from left to right. And when your base is between 0 and 1, your graph is decreasing from left to right. And it's true even if, and I'll answer that, I'll look at that other asymptote question. It's true even if your base is like still kind of not even that much longer. Like if you were graphing something like y equal to 1.02 to the x power. I mean, the values here are not going to get big very fast at first, right? Like 1.02 squared is something like 1.0401, I think. Right? Like it's not much bigger. Like, so your values don't increase very fast, but eventually even this one does get bigger and bigger, which is why I don't encourage you to like make a scale on the x or y axis, because then no one can be like, oh, your graph looks wrong. But to kind of show you what that looks like on Desmos, just so you can actually see what it looks like. Right, it looks very flat. It looks kind of like it's a straight line. You're like, James, you're lying to me. I'm not. I would never do. I never on purpose lie to you. If we zoom out, oh yeah, look, that thing gets really big. It just takes a while. So even things with bases that are pretty close to 1 eventually get exponentially large. Or if they're a little bit less than 1, they're large to the left instead of being large to the right. But any exponential function where the base is a constant and the exponent is the variable x, get very, very large eventually, either to the right or to the left, depending on if your base is bigger than 1 or smaller than 1. So yeah. Someone asked me to explain more what an asymptote is. So an asymptote, well, there's 2 different kinds of asymptotes. Well, that's not true. There's actually an infinite number of kinds of asymptotes, but there's 2 or 3 kinds that we deal with commonly in graphing. Those are horizontal asymptotes, vertical asymptotes, and sometimes with rational functions, slant asymptotes or oblique asymptotes, as some people call them. As far as a horizontal asymptote, which is what we're talking about here, is concerned, a horizontal asymptote is a value, a y value, that the function gets very, very close to as x gets large. Now, x can either get large in the positive or in the negative direction. So we usually say this as x goes towards infinity or as x goes towards negative infinity. So in this example, y equals 0 is the horizontal. So in all of our examples so far, y equals 0 is the horizontal asymptote. And in this one, it's because as x gets very, very negatively large, the y values get very, very, very close to 0. Again, for example, if x were to equal, say, negative 1,000, then our y would be 1.02 to the negative 1,000 power, which is 1 over 1.02 to the positive 1,000 power. And I don't know what 1.02 to the 1,000 power is. Let's find out. Let's pull out the good old trusty calculator. 1.02 to the 1,000 power is about 400 million. So this number here, 1 over 1.02 to the 1,000 power, is about 1 over 400 million, which is very tiny, very close to 0. So as we move out to the left, the y values get closer and closer and closer to 0. So a horizontal asymptote is just a number, a y number that the graph gets closer and closer to as you move further and further away from the origin in either direction, or maybe even both. Sometimes the function will have the same horizontal asymptote in both directions. We should do some more examples though, because there's still a few things to talk about. Yeah. Okay. So yeah, graphing things like this is pretty much a process where you just kind of throw, I mean, there's not really more to say other than you just kind of draw the thing, which I know sounds kind of not very helpful, but it's going to have the usual shape. So if I was going to graph, like y equals 10 to the x, okay, there we go, boom, 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 graphed. And if you wanted to make it look more precise, you could actually try and draw it to scale, meaning you could actually try and draw your next point. So it really was over 1 and up 10. The problem is that gets challenging if your numbers are really anything larger than 4 or 5, right? If I was going to actually try and draw y equals 10 to the x more accurately, say, okay, I'm going to go over 1 and I have to go up 10. So 1, 2, 9, 10. So this is my point, and then this is my next point, and I have to draw it so it doesn't look like it's right. Oh boy, right? See, I certainly don't need you to try and be that precise, because the problem with this is when I draw this, this looks too straight. It's not supposed to ever be a straight line. It's supposed to have curvature to it. It's just really hard to draw it curved without having it accidentally go back on itself, which is not allowed to do. On the homework, I only need you to graph the y-intercept and also make sure you have the horizontal asymptote correct, meaning in this particular example, y equals 0 is the horizontal asymptote. But I do not need you to try and be this precise, because I am not good at it. I don't expect you to be good at something. I mean, that's not true. I expect all of you to be all kinds of good at things that I'm not good at. But specifically when graphing, if I'm not able to do it relatively easily, I don't expect you to either. So yeah, just the y-intercept. That's kind of all you need, really. Now, there is one really important exponential graph I want you to do. Actually, I forgot to do one that I meant to do. So let's graph y equals 5 to the negative x. So we didn't talk about a negative x. Well, that's because we didn't need to, because y equals 5 to the negative x is really the same as y equals 5 to the negative 1 to the x, and 5 to the negative 1 is 1/5. So I get y equals 1/5 to the x. And since my base is smaller than 1, I know it's going to be decreasing from left to right. So the graph of this is going to look like, now again, if you want to be really kind of precise, you could say, okay, well, I'm going to get the point 0, 1, and then I'm going to get the point 1, 1/5, and right, because if x is 1, y is 1/5. And if x is negative 1, y is going to be 1/5 to the negative 1, which is 5. So I could try to be more precise here. I don't need you to do this though. So those are the 3 points that my usual curvy shape should go through. My usual curvy shape. Okay. Just kidding. I don't really have a curvy shape. I mean, I got some curves, but not like what people mean when they say people are curvy. Okay, so that's all right. That's not my best. I would much prefer just to draw it like this. No, wow, I missed. That's all right. There we go. That's, to me, just as good as the previous one, if not better. Try not to draw it too straight. Try to make sure it's got the right kind of shape. But all the shapes are either this shape or the flip shape, right? They all look like. Let me close this for a second. Right, they all kind of have this exponential look, and it is very specific to exponential functions. No other kind of function has that kind of shape. There is a very important exponential function. I should say, really, oh my gosh, brain work, no, brain. There's a very important exponential base. So the number e, the number e being approximately 2.71828. There's more digits to that, obviously. It doesn't stop there. All you really need to know is e is approximately 2.7. It's between 2 and 3. It's closer to 3. E is the most important, well, maybe second most, maybe the most important base. 10 is also very important, right? 10, we're a base 10 kind of world in a lot of ways. So base 10 comes up a lot, but E is kind of probably the more important base. At least when it comes to calculus, E is where it's at. So if I was going to graph y equals e to the x, it's going to have the same sort of properties. In fact, I think you might be, I'll graph it here. Fine. I do want to graph this one semi-precisely just so you can kind of see how it looks. So I'm going to plot the point 0, 1, and then I'm going to plot the point 1, comma e, right? Because if x is 1, y is going to be e, which is approximately 2.7. So I'm like, okay, it's about like there. And then I'm going to graph it. There you go. There's y equals e to the x. You will definitely be seeing a lot of this function in calculus, for sure, all the time, 100%. It's got the same sort of properties, right? Still has a y-intercept of 1, horizontal asymptote at 0, domain is everything, range is all positive numbers. I will say something about this that's true, but you shouldn't worry about it. And the thing that's true is, of all the exponential functions that look like some base to the x power, 2 to the x, 3 to the x, 5 to the x, 10 to the x, 1/3 to the x, etc. This one is the only one of those that if you drew the tangent line to the graph through the y-intercept there at 0, 1, the tangent line would have a slope of 1. Every other exponential function, the tangent line through the y-intercept has a different slope. But this one is special. And although that might not seem like that big a deal, it's kind of a big deal. So we'll definitely revisit that when we take calculus. All right. So I definitely have not gotten to all the things I want to say today. That's all right. We still have next week as well. Also, I can make some more videos as well. So let's talk about shifts and reflections for just a second. We actually kind of already talked about one reflection, right? So if I want to do a reflection in the y-axis, I'm going to put a negative on the x. So y equals 2 to the negative x is the reflection of y equals 2 to the positive x. And we can already kind of see this. Here's y equals 2 to the x, looking good, like it should. Other words that rhyme with good, okay. And y equals 2 to the negative x. Well, y equals 2 to the negative x, we've already kind of seen this, is y equals 2 to the negative 1 to the x, which is y equals 1/2 to the x, which definitely looks like that, except it's flipped over because it's decreasing from left to right. Whew, yeah, okay. And these are definitely reflections of each other in the y-axis. You can also see it on the good old Desmos, right? If I was going to, let's do that. Ooh, let's zoom in. Let's go home. Click the home button, it kind of recenters you with the usual screen, right? If I do y equals 2 to the negative x, oh, look, those are exactly symmetric to each other, right? One of them is the flip of the other one. You can also see that 2 to the negative x is literally the same as graphing 1/2 to the x, right? Same thing, the green one, the blue one, the blue one, the green one, right? Same thing. So yeah, that's your horizontal reflection. And then we also have a vertical reflection. And I want to address this not really because I care so much about the reflection, but because I want to show you something to make sure you don't like get all twisted about something. Yeah, what am I doing? Why is that not doing it? Okay, fine. Okay, so we can also do a vertical reflection, like, so again, I know it's been a while since we talked about graphing trig functions, but if you want to affect the graph horizontally, you do something on the inside, like we did here, right? We did the negative on x before we did the 2 to the power of. Here, since we want to do a vertical transformation, we are going to do something on the outside of the function. So we're going to do y equals negative 2 to the x. And what I want to stress here is that we do not have a negative base, right? Y equals negative 2, whoops. Negative 2 to the x. This is not the same. Y equal to negative 2 to the x. Negative 2 to the x just means you first do the power and then afterwards do the negative. So we could plot some points if you wanted to, real quick, like here. X 2 to the x and negative 2 to the x. Let's just do it real quick. Negative 2, negative 1, 0, 1, 2. If x is 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4. And then the negative of 2 to the x is literally just take those 2 to the x values and make them negative. Negative 1/4, negative 1/2, negative 1, negative 2, negative 4. So I really want to emphasize, right? When you have a negative base to a power, if there aren't any parentheses telling you to do anything in a specific order, you have to do the power before you do the negative. So negative 2 to the third without any other instruction must be negative 2 to the third, which is negative 8. So just be careful about that. And so this one's going to look like, well, instead of having all the positive values, I'm going to have all the negative values. So my y-intercept is now 0, negative 1. It's going to look like this. There is y equals negative 2 to the x. And so if you have a negative in front, it's literally going to have the same sort of shape as it normally would, just flipped over. So we can just as easily draw y equals negative 3 to the x. And again, I'm just using the same sort of idea that I'm going to take the usual kind of shape and then just flip it over. So I'm going to have that, and then I'm just going to draw away. Got to make sound effect when you draw, right? You can't just draw, you have to go. Okay. Wow, what else did I want to say here? So reflections, no big deal. Oh, then I guess you could do both reflections at once. Oh, there's a chat. I should look at the chat. Excellent question. So in each of these still, the horizontal asymptote is still 0. So this one, yeah, good, very good question. Horizontal asymptote is still 0. horizontal asymptote is still 0. Not to, right? Everyone we've done so far, the horizontal asymptote is still 0. I know we're almost out of time, so let's do an example where the horizontal asymptote isn't 0. And the way that's going to happen is if you shift the graph up or down. So an example, I want to graph y equals 3 to the x plus 5. So the entire graph is just going to move up 5. So instead of being your normal y equals 3 to the x with a y-intercept of 1 and a horizontal asymptote of 0, everything's going to increase by 5. So that's going to move up 5 to the 0.06. And this point here, which is 1,8, would move up to the point, sorry, I was getting ahead of myself. 1,3 is what it would be in the original graph. It would move up to the point 1,8. So it could look kind of like this. What's my new horizontal asymptote there going to be? Well, the old horizontal asymptote was y equals 0. And if I'm moving everything up by 5, if I move 0 up by 5, my new horizontal asymptote is going to be y equal to 5. So my new horizontal asymptote, which we do draw with a dashed line if it's not the x-axis, is y equal to 5. And then I'm just going to draw the thing like this. And my new y-intercept is 0.6. So if you shift the graph up, the horizontal asymptote shifts that much up. So if you shift the graph up by some amount, the new horizontal asymptote is just y equal to that number. If you shift the graph down by some amount, the new horizontal asymptote is just that number. So let me do, I know it's 2:20. I'm going to take 2 more minutes. We'll do this last example. Now, there are plenty of examples in the notes that we didn't quite get to. I mean, not plenty, there's a couple. I will mention, typically for myself, I only really care about asking you about shifting exponential graphs up and down. Left and right is not that big deal. Ah, excellent. Oh, great question. I love it. Yeah. So, well, let's see. What's the lowest value we could get? How low does the graph go? Kind of like a limbo, right? How low can you go? How low can you? We can get almost all the way down to what y value? Well, I can't quite get to 5, but I can almost get to 5. I can get to as close to 5 as you want to get. That's why it's the horizontal asymptote. So the range here, that's such a good question. Thank you so much. The range here is everything from 5 exclusive to infinity. Or if you prefer, you could say the range is y is bigger than 5. Can't be equal to 5, but you have to have every number that's just a tiny bit larger than 5. So 5.01, 5.0001, right? Anything that's just that much bigger than 5. Yeah, good question. Excellent, excellent question. I can't say enough how great that question was. All right. So one more example for you all, and then we might do a couple more examples next week on Tuesday. I would really encourage you. I know it's a long weekend because we don't have any class on Monday. Also, yeah, I'm taking tomorrow off. So, so even though I'm taking tomorrow off, I'm still very available by email. So if you have questions, you want to email, you can also write a discussion on Canvas. I know something we haven't really used this quarter or this session, but if you want to do that, I'm happy to respond. I do respond well. So yeah, so if you have questions, do feel free to ask them via email or to other people in office hours. Anyway, let's do this last one. So this one's going to shift down by 8. So we're going to take our regular graph that would look like this. We're going to move it down 8. So my new y-intercept is going to be 0, -7, which you could either find by saying, well, it's 1 minus 8, which is -7, or you can just plug in 0. If you plug in 0, 4 to the 0 is equal to 1, and 1 minus 8 is 7. So the y-intercept is set x equal to 0. You get y equal 4 to the 0 minus 8, which is 1 minus 8, which is -7. Cool. Okay. going to try not to be super precise here. I also know my new horizontal asymptote is going to be y equal to -8. Because we're just taking our horizontal asymptote of 0 and subtracting 8. 0 minus 8, right here. That's how we're getting the new one. We're taking the old one, we're subtracting whatever the shift is, we're adding whatever the shift is. So here's my new horizontal asymptote at y equals -8. Here is my intercept, my y-intercept at -7. And then my graph is going to have the usual shape. Now, I should ask you all, what does this graph have that none of my other graphs have had? As an x-intercept. I don't think on the homework they actually ask you all to find the x-intercepts for the graphs that have them, but I am going to show you how to find it here because it is something that's worthwhile. So if I wanted to find the x-intercept here, what would I do? I would set the thing equal to 0. So, or I should set y equal to 0. So to find the x-intercept, I'm kind of out of room here. I guess I can do it over here. Sorry, I didn't use my space very efficiently here. So to find the y-intercept, I'm going to set x equal to 0. So, sorry, whoa. That is what you would do to find the y-intercept. But what am I actually trying to do? Trying to find the x-intercept. Woo, come on, James. Trying to find the x-intercept by setting y equal to 0. All right. So if I set y equal to 0, I get 0 equal to 4 to the x minus 8. I'm going to try and isolate the 4 to the. I'm really going to try and isolate the x. I'm going to write this as 8 equals 4 to the x. Oops, 4 to the x. So 4 to what power equals 8? So this is a case where we really like a logarithm, which we'll talk about on Tuesday. But here you can recognize that 8 and 4 are both powers of the same smaller common base, which is 2. You can write 8 as 2 to the third, and you can write 4 as 2 squared. So 4 to the x is 2 squared to the x. And then when you have a power to a power, we multiply the powers. So we end up with 2 to the third equals 2 to the 2x. And then if the bases are the same, which they are now, the only way for these two expressions to equal each other is for the exponents to be the same. So we have to have that 3 is equal to 2x, which means 3 halves is equal to x. That is our x-intercept.